the angular velocity of the rigid body. To calculate that, let us take two straight lines 1 and 2. Let them make angles theta and beta with respect to this fixed reference line x and x dash. Let us assume that the angle between these two straight lines is phi. In the triangle ABC, we know that beta is equal to theta plus phi. Sum of these two internal angles will be equal to this angle. This is a simple geometrical idea studied in 10th standard. You would have studied this. Taking the derivative of both sides with respect to time, we can write d beta by dt is equal to d theta by dt plus d phi by dt. Since the straight lines 1 and 2 are fixed, when these two straight lines are fixed, the angle between these two straight lines phi, that does not vary with respect to time. Phi is a constant quantity. Why? Because the straight lines are fixed with respect to the rigid body. This is the rigid body. In this discussion, not to complicate the matter, we have taken the plate-like structure. Plate-like structure, that is called lamina, or plate-like or plate. So when phi is constant, d phi by dt is 0. So this term will vanish. And according to the concept of angular velocity, d beta by dt is the angular velocity of the straight line 1. Because with this rate the straight line 1, it's not straight line 1 of course, beta is the angle or angular position of the straight line 2. So d beta by dt is the rate of change of the angular position of the straight line 2 with respect to this fixed line. That is the angular velocity of the line 2. That will be equal to d theta by dt is the rate at which the straight line 1 changes its angle of orientation theta with respect to the straight line x dash, and that is what we write omega 1. So these two angular velocities are exactly equal in both magnitude and direction. Hence, we can say that angular velocity of all or any straight line or angular velocity of all straight lines at any point of time or instant are equal to each other. Omega 2 is equal to omega 1. If I draw another straight line, 3, it will be equal to omega 3. If I draw another straight line, 4, its angular velocity is omega 4 will be equal to omega 3. In this way, all straight lines drawn inside the rigid body or on the plate will rotate with same angular velocity, and that common angular velocity is called the angular velocity of the rigid body. Angular velocity of all straight lines at any point of time or instant are equal to each other, which is defined as angular velocity of the rigid body. So, when somebody will ask you what is the meaning of angular velocity of the rigid body, for this assumption of the laminar structure of the plate-like rigid body, when it changes its angular orientation or when it rotates in this plane of the board, we can define its angular velocity as the angular velocity of any straight line drawn inside the rigid body. So, angular velocity of the rigid body is the rate at which any straight line drawn inside it changes its angle of orientation with respect to the reference fixed line. Under this assumption, plane structure or plate-like structure rotating in the plane of the board, we do not consider 3D or three-dimensional rotation. With this great idea, let us discuss a simple example. Well, after defining the angular velocity with respect to ground, we can give an example of a rod which is rotating in vertical plane under the constraint of two surfaces. One is vertical surface and the other is horizontal surface. Let the rod occupy this position. Let us take an angle with respect to vertical or y direction. If the rod slides in this way, the last point of the rod moves with velocity v. Find angular velocity of the rod. The concept is with respect to the reference line. This is the reference line. You may take x-axis as a reference line also, it is your wish. I take y-axis as a reference line. With respect to this axis, a line, the rod, which itself is a straight line, or any line run inside the rod goes along the rod itself. This line makes an angle theta with respect to y direction or y axis, or this reference line, vertical reference line. At what rate this angle is changing with respect to time? That is the angular velocity of the rigid body, the rod. This is the concept. Of angular velocity measured by ground frame method. Let us assume that this is the origin and the last point has the position x along x direction. If the L is the length of the rod, x can be written as L sin theta. Once you have the relation between this linear dimension and this angular dimension, the linear position of this point 1 and the angular position of the rod with respect to the vertical, then we differentiate both sides with respect to time to get dx by dt equal to L. The derivative of sin theta with respect to time can be written as cos theta d theta by dt. Our kinematics, linear kinematics, says that dx by dt, when this point moves in the increasing order of x, dx by dt can be written as plus v. And using the latest concept of the angular velocity, when theta is increasing, d theta by dt can be written as plus omega the L cos theta. This gives us omega is equal to v by L cos theta. Answer. So, in this problem, you may take x axis as a reference line. If you wish, and with respect to the reference line, let the rod make an angle, suppose beta. With this method also you can do. Method 1, you take y axis as the reference line, and method 2, you may take x axis as the reference line. But both the methods, maybe the methods are different because you have taken different reference lines. But actually, the concept is same, that is called ground frame method. In method 2, x can be written as L cos beta. Differentiating both sides with respect to time t once, you can write dx by dt equal to L cos beta derivative minus sin beta d beta by dt. Since this point 1 moves towards the right, x increases. Therefore, dx by dt conventionally we can write plus v is equal to minus L sin beta. When it moves in this way, the beta decreases. Since beta decreases, d beta by dt can be written as minus omega. So, omega can be written as v by L sin beta. Theta plus beta can be written as pi by 2 radian because this is a right angle triangle, because these two surfaces are perpendicular to each other. One is horizontal surface, another is vertical surface. V by L sin beta. So, beta equal to pi by 2 minus theta. You can substitute here to get sin pi by 2 minus theta. Ultimately, you are getting same answer. Isn't so? Oh yeah, you are getting same answer. Therefore, in both the processes, whether you take this as a reference line, x-axis, or you can take a y-axis as a reference line, you are getting same answer. But both the processes are based upon the concept that omega rod is equal to the rate at which the angle of inclination of the rod with respect to either x-axis or y-axis or any other line changes its angle of orientation. At what rate? That is the angular velocity of the rod. Well, I can support this concept by taking another example. Well, let us take another example. In this example, let us take the rod which is rotating in vertical plane under the constraints of two surfaces perpendicular to each other, but here there is a change. The upper end of the rod is not constrained to move along the surface, along the vertical surface. There is a tip and the rod is also sliding over this tip. When you pull the bottom end of the rod towards right along the horizontal surface. So, here you need to calculate the angular velocity of the rod. Let this angle be theta. I am taking the angle in such a way that when the rod moves or rotates, this angle increases. Then only you can write d theta by dt is plus omega. If you take this as the angle theta or phi, the rate of change of this angle will be equal to minus omega, because this angle decreases. If h is the height of this portion or the roof, we can write the position of the bottom point of the rod with respect to the origin as x is equal to h. X by h is equal to tan theta. X by h is equal to tan theta. So, x is equal to h tan theta. H is a constant quantity. Differentiate both sides with respect to time. Dx by dt is equal to h. Derivative of tan theta is secant square theta d theta by dt. Since theta increases as the rod slides towards right, d theta by dt is equal to plus omega. Since this point moves towards the right, x increases, then since x increases, dx by dt is equal to plus v. With these ideas, we can write v instead of dx by dt is equal to h secant square theta. Instead of d theta by dt, we can write plus omega is plus v. So this gives us omega is equal to v by h cos square theta. This is the answer. It's a nice problems. You can get the same answer when you take this angle as a reference angle beta and convert beta to theta by writing beta is equal to 90 minus theta. So these are all the problems we are solving by taking the coordinates or the positions. It may be linear position of this point, or it may be angular position of the rod with respect to the fixed line, that is the vertical line or horizontal line with respect to ground. Therefore, this method is called ground frame method. Let us now come back to analyze and understand the direction part of the angular velocity. Angular velocity magnitude you calculated. If I recast the other problem, the first problem, where the rod rotates under these two constants. Here also the rod is rotating under these two constants, but there is a difference. The upper part of the rod, there are 2 points of the rod in contact with the surfaces. This point is in contact, this point is also in contact, but here there is a projection. The bottom, the lowest position or lowest point and the highest point of the rod are sliding along x-axis, along y-axis respectively. But here the lowest point is sliding along x-axis, but the highest point is not sliding along a particular straight line. Of course, you can ask, what is the nature of motion of this point? This is a nice question. We can do that. But before that, let me make some sort of comparison between these two problems. In common, how to calculate the direction of angular velocity mathematically. Here you wrote x is equal to L sin theta and omega you got V upon L cos theta. Well, since this is positive, this is positive, omega is anticlockwise. Since this is positive, this answer is positive. Answer is positive. Omega is anticlockwise. Now a question arises. When you write omega as a vector quantity, any vector quantity, say with respect to the origin, position of the mango, this is given by a vector quantity, that is called position vector, and that position vector has one head, one tail, and that is with respect to this origin. So we can say position of the mango with respect to the origin. Now one thing you can ask me, angular velocity of the object with respect to which axis or which point? That's a great question. Angular velocity with respect to which axis or which point? Angular velocity does not depend upon any reference point. Therefore, about which point, it doesn't make any sense. About all the points, angular velocity of a rigid body at any instant remains the same. At a given instant, angular velocity of the rigid body about this point P, about this point Q, about this point C, about this point A, about all the points, with respect to all the points, angular velocity of the rigid body or of the rod are same or is same. So angular velocity does not depend upon any reference point. This is a great concept. Angular velocity of a rigid body does not depend upon any point, any reference point or a reference axis. It is an internal property of the rigid body. It is an internal property of the rigid body. This is an important concept. So I would like to emphasize on this point by taking few examples. Then I can put a theory on this, a theoretical analysis on this. Angular velocity anticlockwise. Student may ask, sir, I would like to write the arrow in this way. Anticlockwise means what? Putting the curved arrow in an anticlockwise manner. Anticlockwise, this is correct, this is also correct. And when you assume this is x-axis, this is y-axis, this should be the z-axis. So, or you can write plus k cap. Angular velocity is directed along positive z direction because it is governed by right hand thumb rule, which states that when the sense of the angular velocity, that is anticlockwise or clockwise, is given by the curling of your finger of the right hand thumb, the extended thumb will give you the direction of what? The angular velocity. The angle changes in this direction. Therefore, angular velocity is anticlockwise, or you can write anticlockwise, or symbolically you can write as a curved arrow which gives anticlockwise sense, or you can write plus kf. But it does not mean that angular velocity of this rod about y axis, about z axis about x-axis is same. Since its angular velocity is pointing along positive z direction, this is positive z direction, positive z axis. If I take another straight line parallel to positive z axis, angular velocity of this rod about this axis also is same thing. Angular velocity of the rod about this axis is also same thing. If you take any axis parallel to the z axis, angular velocity of the rod remains unchanged. In that way, angular velocity of the rod or the rigid body doesn't depend upon the axis. However, its angular velocity points in along a particular axis or parallel to a particular axis. So you can just write angular velocity is equal to V by L cos theta. This is the magnitude part and this is the direction part. So this is the complete vector expression for the angular velocity. And the component of the angular velocity of the rod along x direction is 0, along y direction is 0. Along x direction or about x direction, same thing. Along y direction or about y direction. There is no projection, no component, no part of this angular velocity of the rod along x direction or about x direction, along y direction or about y direction. The angular velocity of the rod is totally pointing along positive z direction. In that sense, we have written that angular velocity of a rigid body doesn't depend upon any reference point or reference axis. It is an internal property of the rigid body. Then I can make it as a general statement, drawing a general diagram. Well, so angular velocity of a rigid body, if it is positive, angular velocity is positive when the rigid body rotates in this way. What is this way? Anticlockwise. And if the rigid body rotates in clockwise manner, angular velocity is said to be negative. This is clockwise rotation. When the rigid body rotates in this way, suppose this is a rigid body, this rigid body, the pen rotates in this way. It is called anticlockwise rotation. Angular velocity is positive. In the sense, angular velocity we can write angular velocity vector equal to omega k cap direction. If this is x direction, this is the y direction, this will be z direction. Well, if this rigid body or particularly this pen rotates in this way, this is called clockwise rotation, or you can write omega vector equal to omega into minus k cap. When it rotates in this way, according to right hand thumb rule, the sense of rotation, when it rotates in this way, this is the sense of rotation given by the curling of the finger. When you rough your finger, suppose it rotates in this way, try to understand. It rotates in this way. You hold your right hand. When it rotates in this way, you rub the finger in the sense of the rotation. When it rotates in this way, you rub the finger in the sense of rotation, and the extended thumb will give you the direction of angular velocity. Either you can say it is positive z direction or plus k cap, or you can say it is anticlockwise. Similarly, when This rigid body rotates in this way, means clockwise manner. So you wrap your finger in clockwise sense, and the extended thumb will be in or in negative z direction or minus k cap direction. This is the clockwise sense or minus k cap direction. It is anti-clockwise sense or plus k cap direction. Therefore, angular velocity can be given as anti-clockwise or clockwise when it is rotating in one plane in front of you or above you. You can say clockwise or anti-clockwise, or along a particular axis. If you take this as x-axis, this is y-axis, definitely the outward axis will be positive z-axis, and the unit vector representing the positive z-axis or along the positive z-axis can be given as k cap. When it is out, plus k cap. When it is in, minus k cap. Out means anti-clockwise, in means clockwise. Either you can just write anti-clockwise. In words you can write anti-clockwise, or sense pictorially, or you can write outward. Duck means outward, cross means in, or plus k cap. This is correct, or this is correct, this is correct. You can choose any one or any two. Similarly, it is clockwise or symbolically by the curved arrow, clockwise, in clockwise sense, or into the board, or minus k cap. You can choose to write clockwise, or you can choose to give this geometrical symbol, the curved arrow, in the clockwise sense, or you can put it into sign, or you can write minus k cap. It's your choice. So by giving the sense, you can write omega. Here omega is anti-clockwise, here omega is clockwise, or here it is outward, here it is inward, or here it is plus k cap direction, here it is in minus k cap direction. And this is the clear-cut idea of the direction of omega. Angular velocity does not depend upon any reference point. Angular velocity with respect to different axes will be same. Angular velocity does not depend upon the axis in that sense. Angular velocity about the central axis, above the axis passing through this point, about an axis passing through this point B, about an axis passing through the point D, about an axis passing through the point E. You can take number of points. If you take all perpendicular axis, about this axis omega is same, about this axis omega is same, about this axis you have same omega, about this axis you have same omega, about the central axis you have same omega. So you can give omega sign here, or you can give omega sign here, or you can give omega sign here, but sense is always anti-clockwise. You can give omega sign here, you can give omega sign here, you can give omega sign outside, but it doesn't look nice. Therefore, different authors have different diagrams, the notations or the presentation of the diagrams. For instance, this body rotates in anti-clockwise sense. This is one representation, and you can take this body moves in anti-clockwise sense. You can give omega with graphical and the symbolic in this way. This is also correct. This is also correct. Or you choose to write in this way. Or you can write in this also. But generally, if you put like this, this is also correct. But generally, we choose this or this. But it doesn't mean that this is centroidal axis. Therefore, I can give you fourth option for representing the same thing. You can take point here in this way also. Take any point and give the correct sense. A anticlockwise, this is anticlockwise, this is anticlockwise, this is also anticlockwise. But this is also correct. But generally, you can give omega sign outside or inside about the center of mass point, or about any point in some sense, or outside also you can give. All the options are absolutely correct representation, and this is a major problem the students are facing about which axis. Angular velocity does not depend upon your chosen axis or chosen point. However, all the axes must be lying along or parallel to the omega vector. The omega vector, if you choose, this is x-axis, this is y-axis, omega vector for anticlockwise rotation is lying along positive z direction. So, any axis, whether this is through the center of mass or this is passing through any other point, inside or outside, doesn't matter. You can take any point outside, about this axis, about this axis, about this axis, about this axis, through all the axes parallel to the z axis, omega remain the same. However, you should give the correct sense. Sense is anticlockwise. So, you can go for this or this or this. This generally, if you give also, this is correct, but we don't prefer. But this doesn't look nice. Well, so this is a conceptual analysis of angular velocity by taking the ground frame method, but it doesn't depend upon the point fixed with respect to ground or fixed with any other point except the ground. Omega is an axial vector. Axial vector is the vector which has no fixed origin, or where is the tail of that vector, where is the head of that vector, nobody can say precisely, but we can say that the vector is existing, a vector is lying along positive x direction or positive y direction or positive z direction, but nobody can say precisely where exactly the vector is directed. Well, let us take another illustration. I take this rail and rotate it. When I rotate it, it rotates. In which sense? It is rotating in anticlockwise sense. Rotation is anticlockwise, or omega vector is representing or lying, or it is pointing along the positive z direction. When I rotate in this way, when I rotate in this way, this clockwise rotation. When I rotate in this way, it is anticlockwise rotation. So, when I rotate it, am I giving some fixed axis? No, I am not giving any fixed axis. Therefore, I can rotate in this way, I can rotate in this way, I can rotate in this way, and I can rotate in this way also. This is quite zigzag. So, rotation of a rigid body does not depend upon whether you have pinned the rigid body or you left the rigid body freely. For instance, if I release it, this rotates, and this point is fixed, kept fixed. So this is the rotation. This is also rotation. This is also rotation. This is also rotation. This is also rotation. So for rotation, it is not essential that you will just keep one point of the rigid body fixed. When you keep one point of the body fixed, it may rotate by changing its angle of orientation. When you don't fix, you just rotate it by giving a twist, angular impulse. The rigid body will go on rotating in the space. Therefore, rotation does not mean that always one of the point of the rigid body is kept fixed or fixed axis. Now question arises, sir, the fan rotate, the blades of the fan rotate. There are 3 blades or 2 blades. The blades of a fan rotate. You can say that the fan is rotating. While doing so, the axle of the fan is kept fixed. That is also rotation. When I rotate the subject or I spin the ball, spinning means rotation. If I spin the ball in this way or in this way or in any way you like, the rotation of the ball doesn't depend upon the axle. We are discussing the physical interpretation of the angular velocity. The ball may rotate in this way. 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 But giving this line doesn't mean that always the axis should pass through the center of mass of the body. This is a wrong concept. I have given this line to show that angular velocity direction is like this, like this. However, this diagram can be drawn in this way also. This omega, same thing. Whether you keep the axis here or keep the axis here, but should be parallel. Same thing. When the ball rotates in this way, rotates in this way, rotates in this way, you are not pivoting or constraining the motion of the rod or motion of the object or motion of the ball like you constrained the motion of the fan. This is the axle or axis of rotation passes through the axle. Axle and axis, this is the mathematical concept, and axle is a physical concept. Suppose you take the axle, the rod, by which the fan hangs from the roof. This is the axle. This is the axis. The blade may rotate in this way. This is the axis, or you can put the axis anywhere, but the axle is fixed. You can take the axis passing through the axle, or you can take the axis parallel to the axle, doesn't matter. About all these axes, the omega remains same. So You may think that, sir, axis is fixed. Axis is not fixed. Yes, you can say axis is fixed because this axis, this axis, this axis, this axis, this axis, this axis, and many other axes parallel to this. They are said to be fixed because the lines or the axis do not change the angle of their orientation. So long as, suppose this is a flywheel is rotating in this way or in opposite way, either clockwise or anti-clockwise. When you just move the flywheel in this way, you are not rotating the axle, you are not changing the angle of orientation of the axle. We can say that this axis is not changing. The axis is not changing. The flywheel or any fan rotating either in anti-clockwise sense or in clockwise sense, either in anti-clockwise sense or in clockwise sense, either out or in omega. When you move your hand such that the axle doesn't change its angle of orientation, like that, keeping all the positions of the axle parallel. In that case, we call it the axis is fixed. When you twist your hand, the axle gets twisted or the axis of rotation gets twisted. So long as the axis of rotation does not change, we can call them omega constant. Magnitude wise, direction wise, so long as the angular speed remains constant, so also the direction of rotation we can call omega vector remains constant. But the moment you change, even though the fan or the disc or whatever it may be, just like a flywheel, rotates with same angular speed, but you keep on changing the axle, the omega vector changes because the direction portion of the omega vector will change. When direction or magnitude or both of a vector change, we can say that that vector is changing. When you rotate the axle, you are changing the direction part, the direction of rotation, the direction of the angular velocity, even though you are keeping the angular velocity magnitude or the angular speed constant. In this way, you are changing the angular velocity vector. And in the next class, I will tell you what will happen if you change either direction part of the angular velocity vector or its magnitude part. Another vector will come into play, that is called angular acceleration.